Hello, in this video we will see the geodesics on Riemannian manifolds. Geodesics are very important because if you need something like the lines in the Euclidean space, you need to find the geodesic on the Riemannian manifold. Also, geodesics are important because its applications nowadays geodesic regression and similar concepts are very important in machine learning theory. So that's why it is important to know how to find the geodesic on a Riemannian manifold. So geodesics on Riemannian manifolds. Okay, so first we have a Riemannian manifold, let's say MG, Riemannian manifold. And we have a alpha, a curve on M. Of course, it's important to mention about the representation of this curve. So if you have, let's say, alpha from I to M as a curve, and we have parameterization for the manifold, let's say Rn. So let's say this phi. So we have phi composite alpha. So when we say the alpha of t, we mean phi composite alpha of t. So it means you have this one, x1 of t, xn of t, because we choose this dimension of the, okay, not Turkish, dimension of m. Okay, so when we mention about the tangent vector of this alpha, we mean x prime 1 of t, x prime n of t. So you can write this one I xi. So this is the frame of this manifold. Also we have a nabla, this is a Levi-Guittard connection. So sometimes we call this one Riemannian connection. So if you have, let's x be a vector field on M, then x is called parallel along curve alpha if nabla alpha prime of t x 0. So if you have this one, alpha, the tangent vector of this alpha, if it is 0, alpha is called a geodesic. On M. So it means the tangent vector of the alpha is parallel along itself. So then we call this geodesic. Now we know how to find the geodesic in classical differential geometry for the surface. So if you remember, we have two equations, differential equations. So we try to solve these equations and then find the geodesics. And alpha is classical to the surface theory. We have two very well-known geodesics. One is the geodesic of the sphere. It's the big circle. And also we know the geodesic of the cylinder. The geodesic of the cylinder is line, helix, or the circle itself. So now we find the geodesic equation for the Riemannian manifold. So let's start this way. Let's say X is a vector field on the manifold XY. So Y is Yj delta Xj. So we know there is a summation on these indices because it appears on the top and the bottom. So that's why we know that this Einstein summation, it is a summation on these indices. So now consider this nabla xy. So we can write nabla xi delta xi yj delta xj. So using the properties of this connection, we can write xi yj delta xj, and then if you take the derivative, first you have this one yj delta xi delta xj plus, so xi nabla xi, okay, let me write this one also, yj delta xi xj. So from these we can write xi yj xi delta xj plus xi yj gamma ijk delta xk. Okay. So the first part, this one is the x yj delta xj plus xi yj ijk delta xk. So we know that these all indices I, j, k runs on the same index set. So we can write in this form x, let's say yk plus xi yj ijk delta xk. So we have this one xy. Now if you choose x alpha prime of t tangent vector, and we can write this one as the x prime I delta xi, and also we choose the alpha of t xj prime xj delta xj. So if you put this here, nabla alpha prime of t equals, so first you have alpha of t xj plus x prime I x prime j gamma ijk delta xk. So we can write here, so this will be x, this will be k, right? So this k. So we have this one x k plus xi xj ijk delta xk. So it means you can write this one. This coordinate derivative is 0 if and only if x k plus xi xj k equals 0, k equals 1 to n. So here, for every k, you will find different equations. So you see these are the differential equations. Of course, we have a summation on these indices I and j. So we can write this theorem. Let M be a Riemannian manifold and x1, xn a local coordinate system on M. Then a curve, let's say alpha, is geodesic if and only if this equation is satisfied, this one. So this is our geodesic equation for the Riemannian manifold. So if you are trying to find the geodesic of any given Riemannian manifold, you need to solve these differential equations. So there is no k here. Okay. Consider one example. Let M be a Riemannian manifold given by let's say U xy belongs to R2 such that y is equal to 0 and the metric is this 1 over y square dx square plus dy square. So this one is called there is a name for this, the Poincare upper half plane. You see, although we have a plane R2, but the metric is not conic metric, so it is not the Euclidean space. So that's why it's called the Poincare upper half plane. So this manifold is called this one. So the question is find the geodesics of M. Okay, first let me write the matrix of this metric. So you see we have this one 1 over y square 0 0 1 over y square, and the inverse of this metric we have this one 1 over determinant this g which is y to 4. So then the adjoint matrix, so we have 1 over y square 0 0 1 over y square. So G2 inverse will be y square 0 0 y square. So we have this one. This is G11, G12, G21, and G22. Also we have this one. So here G11, G12, G21 and G22. you see G12 and G21, which is same, are 0. So first we need to calculate the Christoffel symbol. So remember, ijk is given by 1/2 G2kr. So delta IR xj delta JR xi minus J XR. Okay. So first let me calculate the G111. So we have this one, 1R. So you have 1R x 1R x minus 11 XR. So because G12 will be 0, so that's why I only consider this one, 1, 2, G11. So G11, G11, 2. So you have G11x. And G11 is, okay, let me see. G1 is y square. So 1/2 y square times G11 y whole square. So this will be 0. So that's why 0. So we have 111 will be 0. Okay, let me find another one. So in this case, 112. Okay, so again, we need to find 2R. So you have 1R x, 1R x, 1 XR. So in this case, we need to find only G22 because G221 is 0. So we can write G22. So we have G12x, G12x, which is 0, G11y. So it is 0, both of them. So 1/2 G22 y square. So minus G11 1/y square so you see 1/2 y square, so 2 times y to -3, so you have 1/y. So 112 will be 1/y. So actually we have only these two items, so the others are similar. So we already find 1, So similarly you have 2, 2, 1 and 1, 2, 2. These are all 0. Also we have this one, 1, 1, 2 and -2, 2, 2 and -2, 1, 1 will be 1/y. All the Christoffel symbols will be 0 or 1/y or -1/y. Okay, now we can write the geodesic equations. So let me bring this formula here, this one. Okay, let me put here. Okay, let me write these geodesic equations. So first, for k equals 1, we have this one. ij1 will be 0. And the second, ij2 will be 0. Okay, now expand to this because we need to take the summation on the indices I and j. So let me find the first one. So first you have x, xj, 1j1 plus y, xj, 2j1, 0. So x plus x is derivative, so square 1 1 1 plus x y 1 2 1 plus okay, now I am here. Y x 2 1 1 plus y square 2 2 1. So this is the first one. So you see we have 1 1 is 0 plus 1 2 1. 2 1 1 will be same, so negative. So negative 1 over y x prime y prime plus y prime x prime 2 1 1. So this will be negative 1 over y plus 2 2 1. 2 to 1 will be 0, so we have only this one. So we have this equation. Negative 2 over y x prime y prime equals 0. This is a geodesic equation. The first one is this. The second, we need to expand this one. So again, 2 prime. So x, xj, 1, j2 plus this derivative y, xj, 2j2. So plus x prime square 1 1 2 plus x prime y prime 1 2 2. So now y prime x prime 2 1 2 y square 2 2 2. Okay, so we have plus 1 1 2. 1 1 2, we have 1 over y. 1 over y square 1 2 2. 1 2 2 is 0. 2 1 2 is 0. So 2 2 2. Negative 1 over y. So here we have negative 1 high y prime square equals 0. So we have the second equation as 1 over y, let's say x square minus square equals 0. So this is the second equation. Okay, let me write it here. We have 2 over y x prime 0 and okay, we have these equations. So we need to solve these equations. So first, consider this one. If x prime t is 0, it means x is constant. Let's say is c1. So then the first equation doesn't give anything. 0 will be 0. The second equation plus 1 over y negative square equals 0. So from this we have over y prime equals 1. So here we can write ln y prime equals ln y. So the derivative of this one, So we have this one, ln y prime minus ln y equals constants, let's say c2, or y prime over y c2. So y prime over y equals e to c2, or you can write this one, y prime equals lambda times y. So from this we can write y will be, let's say, c3 times e to lambda t. Now this, so we have this one, constant, let's say c1, yeah. So c3 e lambda t. So we need to find this lambda. So we use this metric because we consider the curve with the arc perimeter. So we can use this metric to measure the length. So if you put here this one, so this should be 1. Okay, dx will be 0, dy will be c3 lambda times e times lambda t square over y itself, c3 e lambda t square will be 1. So from this we find the lambda negative and positive 1. So y becomes c3 e negative or positive t. So our equation in this case becomes this one, this constant, and this one is c3 e times t. So you see this line. Perpendicular x-axis. So we find the one geodesic. This geodesic is the passing for the line passing from the x-axis as a perpendicular, as an orthogonal. So now we consider this one if x prime will be 0. So if x prime is not 0, then we consider this one, d over dt y prime over x prime. So if we take the derivative, we find this one, x dot times y square plus y times second derivative minus x derivative times y prime over x dot square. So derivative ratio. Okay, so first let me arrange this one. X, y square, x, y, this one, minus x, y prime, y dot over square. So now we will use these equations. Which one? The geodesic equations. So if you look at here, from these equations, we can write by using the first equations, we have x, y equals 2 times x dot y dot. So from here, second equation equals negative x square plus y dot square. So if you put this information into the above equation, then we have y over x dot equals, so let me leave this as it is, plus now y 2 dots, so x times negative square y square and negative y 2 times y dot over x dot square. Now if you arrange these equations, y square minus dot 3 plus y square 2 times x dot y dot square over x dot square. So you see these and these cancel each other. If you cancel this one, you have negative x dot. So we find this one, d over dt y dot over x dot equals negative x dot. So from here we have this one over x equals x plus some constant. So we use C3. Now let's say this C4. Okay, now we obtain this one. C4 x prime. If you multiply this by 2, so you have this one square derivative negative x square derivative plus 2 times c x derivative. So from this we obtain this one. Okay, now if you arrange this one, we have this one x square plus y square minus 2 times c4x equals c5. Or you can write this one x minus c4 square plus y square, so x square minus 2 times c4x plus c4 square, so it will be c4 square equals c5. So from this we obtain this one x minus square plus equals, let's say c6. So this shows this is a circle with center on the x-axis. So we find the two geodesics. One is line perpendicular to the x-axis, The other one is circle. The center of this circle is on the x-axis. So we have two geodesics for this manifold. You see, if even for low dimensional, it takes a long time to find the geodesics, but this method is clear how to find these geodesics. Of course, if you use some properties like I did here, it will be easy. Otherwise, if you use analytical techniques from differential equations, it will take more times and maybe more effort.